Okay, well, welcome, welcome to everyone that's here. Thanks so much for attending. I know it's a busy time for a lot of people, but we really do appreciate you coming out and spending some time with Tim and I. As process analyzer folks, we spend a significant amount of our time in combustion control, uh, ostensibly probably the #1 gas analyzer measurement on the planet. So for those people involved in gas analyzers, you tend to always, at some stage in your career, get involved in combustion control. And certainly from my perspective, now that I'm running into my 4th decade in process analyzers, I've spent a significant amount of my career in and around the various forms of combustion control. In the last 20 of those years, I've been lucky enough to spend a lot of that time with AMETEK Thermox, both directly and indirectly over the years. And it's been a good journey for me and a great learning curve. They're a fantastic company. They lead the industry in combustion control measurements. So that's been excellent. The one takeaway for me, which has been extremely useful over the years, is that AMETEK are not a one-size-fits-all analyzer company when it comes to Thermox. They've made many flavors of that analyzer over the time, and many flavors of the various components and bit parts to be able to solve all the complex applications that come along in combustion control. And that really is where we want to kick off today, because over the years they've made a version of their analyzer called the HP, and it remains in the analyzer world unique. It's unique to AMETEK that they have made this kind of combustion control analyzer, and as they've stepped forward into making a new version of that analyzer in the last year or so, we thought it would be a great moment then to gather and have a conversation about what that analyzer is, where it fits in, what the new one looks like, and a whole bunch of other things. So as it's been launched in the last year, we've had a number of people come forward with a bunch of questions, both internally from people trying to sell the product, and externally, certainly, perhaps more importantly, from my customers about what it is, how it works, where it fits in. So Tim and I, and I'll introduce Tim here in a second, have compiled a list of the top 10 questions that we both get asked on a regular basis about what the HPII is, where it fits into the broader industry of combustion control. And we've put them in a chronological order, so they make a little bit of a sense in terms of if we want to give this as a handout. We're very happy to give all our material out to anybody online, so we can PDF it and send it off. So we put it in a chronological order to make a little bit of sense as we send material out. But the idea here is that Tim and I will sit and have this sort of discussion of these top 10 questions, answer those questions, open ourselves up to anyone online that has any more questions that they want to add. Either put it in the chat or raise your hand as we go along, and we'll keep an eye on that, and we'll certainly leave some space at the back end for it. So I spend a lot of my time talking about combustion control for Novatech here in Canada. We're the distributors for AMETEK Thermox, and we spend a lot of our time talking about it. But I'm very happy to have my great friend and colleague and expert, Tim Tallon, who is the product manager for Thermox at AMETEK, with us today. So I'm going to largely hand over to him as the true expert in this field. Tim's got a great wealth of experience. He's spent a long time at AMETEK now, but prior to that, his knowledge of combustion control and combustion efficiency is an added bonus to not just how the analyzers work, but how the industry and the applications work. So we're very happy to have Tim. And we thought it would be a good idea here today to sort of talk about the merits of HP, why it was built by AMETEK in the first place, and then show you the new version of it and what it's capable of doing. So thanks, Tim. Thanks for being here. We appreciate you spending some time with us. We know you're a busy man. So anything you want to add before we get going here, Tim?
Well, thanks for letting me join you. Stuart, happy to talk about the HP and really happy to dive into the top 10 questions. I know that from a agenda standpoint, that is the focus for today's meeting, is just those top 10 questions, things that we've heard that we get all the time related to the HP version of the analyzer, and then also things that we think would be valuable to viewers. The only other thing I think of is just like you mentioned, just emphasizing if there's any questions during the call, we're happy to entertain that, and also there's going to be time at the end for any other questions.
100%. Thank you, Tim.
Shall we begin?
Let's get going. Let's do it.
Cool.
All right, so let's start from the top then. Because as I said in the beginning, it is unique to Thermox. Nobody else quite makes an analyzer like this. So why don't we just explain from the beginning, what is the HP analyzer that Thermox have made?
Sure, that's a great question, Stuart. And just to put it in perspective, there's 4 key analyzer types for combustion control. There's the in situ type, there's the closed couple extractive type, the extractive type, and then the close-coupled convective type. And so the HP is a convective type of analyzer, close-coupled on the process flange, designed to support high particulate applications. It's a pretty nuanced measurement that doesn't have any aspirator, and that's one way to handle those high particulate applications. So in a nutshell, that's the HP.
That's awesome. But obviously, you know, that's all, you know, well and good from a newbie's perspective, let's say. You know, if you're familiar with most, you know, combustion analyzers, they're either in situ, as you say, and you know, it's directly in the measurement, or, you know, you're on the outside, but then you have to have some kind of motive force to get that sample out of the process and into the analyzer. So, you know, how is the HP achieving that then if you're not going to use the aspirator, which is the big difference between that and every other combustion analyzer on the planet?
Yeah. Aside from the question, what is a HP analyzer? This is probably the second most biggest question that I get. And it comes back to almost the best of both worlds. A lot of people are familiar with the in situ type, as you mentioned. A lot of people are familiar with close-coupled extractive type, where it has an aspirator that's pulling the sample. And if you take the WDG-4, the predecessor to the WDG-5, the WDG-4, in the simplest of ways, as you can see here, it has an aspirator. That aspirator is the engine that's pulling the sample in, and that's creating the suction that's pulling a sample from the process through what we call the fast loop and right back out to process. And in the path of this, there is what we call this convective loop. And this convective loop is really important because while 100% of the flow goes through the fast loop forced through by the engine, the convective loop has about 30% of that flow. So it's a lot less to reduce particulates, it's a lot less sample past the detectors. As a result, it helps for reducing plugging for lower amounts of particulate. But that engine, the aspirator is really that engine in the process. If you think about it though, connecting the process to the analyzer is that aspirator. So just building on what you said, and that's what enables faster response time, and that's what enables a measurement in this way. But you asked, okay, well, what about convective? Well, before I go there, let me just talk about in situ type. Now, Stuart, okay, we have the process itself. We have an in situ. Okay, my question to you, Stuart, what's the engine here? What's that motive force that's connecting the process to the analyzer? Because this is a different question. There's no aspirator here.
Right. So if you're in situ, you know, it's the force of the gas just flowing past the end of the probe with the sensor inside it, right?
Right.
Gas flow.
Right. That gas flow. In the transport phenomenon word for that would be like diffusion. It's the diffusion. It's the diffusion migration from the process to the detector itself, make the measurement, and then the diffusion back out. And it certainly has a place in a lot of high particulate applications, especially difficult ones. The challenge is, though, diffusion's slow. I mean, Brownian motion is very slow. It's a very slow process. Even with high velocity stack or high velocity firebox, it's still a challenge to ensure that that measurement is going to be made on time and within time. So when we, as AMETEK Process Instruments, were developing the in situ, when we were developing the HP analyzer, we thought about the in situ. We thought about the close-coupled extractor. We thought about how they could kind of come together to create a whole new analyzer. And so an in situ has that diffusion through the filter. There's diffusion, okay, it's gradual, but it's a way of getting a motive force, a way of getting the sample to the sensor and back. Okay, but I mentioned that there's this convective loop, right? I mentioned in the close-coupled extractor type that there's this convective loop. There's a very high-temperature furnace. That high-temperature furnace enables the zirconium oxide measurement, but there's other advantages of this convective loop. There's the advantage of additional measurements, like a combustion measurement, like a methane measurement, and also the fact that it's right on the process flange. There's no added sample line, there's no added delay in a measurement. And if it's high particulate already, it's already hard and difficult to measure. So it helps to have it on the process flange. All right, well, putting it together, the benefits of an in situ type with the benefits of close coupled extractive type, you get what we call the convective type. And the convective analyzer uses a combination of both. There's diffusion through the filter, similar to that of an in situ, but there's added motive force of this high temperature furnace. And that high temperature furnace is that convection. Just as the convection worked here in a close coupled extractive, that convective type is also pulling the sample in. So in addition to diffusion, there's the convection, the heat of that furnace that's pulling up and creating a flow, even with particulate, that's creating a flow and up and around and back out. So the advantages, so as you can see, like the advantage is also added measurements, like you can see in combustible measurement here, and also having it on the process flange. So kind of putting it all together for an HP analyzer, specifically the HP II analyzer, WDG-V HP analyzer, it's diffusion and convection that enables a faster response relative to an in situ, but also the ability to endure high particulate environments with added measurements with easier serviceability. So I hope that answered your question.
Yeah, absolutely. And I think it's also, perhaps worth highlighting here that, the unique nature of the Thermox product in general with its two loops. You have under the regular analyzer, the WDG-V not the HP version, you have your aspirated loop, but you also have this convection loop anyway. So we benefited from our design. It's an extension of our already existing design, which is quite clever, I think.
Yeah, very unique, very unique.
Mm-hmm. So with all that said, then Tim, then obviously the next question logically then is, okay, there's some complexity here. There's a little bit of redesign inside the package. There's also a trade-off. We have to be honest that it slows down without an aspirator. You're a little bit slower, right? There's no doubt about that. So then, why was it made? What was the real purpose? Where did AMETEK at the time, both before yours and my time at AMETEK, saw the value then in making a high particulate analyzer?
Right. So it didn't happen it may have been fun building, but it didn't happen by accident, right? It happens for a reason. And so as we think about applications, and AMETEK has over 50 years of experience, especially within Thermox, within combustion control. And really, when you look at it, the selection for analyzers really depends on the application. And when you think about high particulate, especially close coupled extractive, like we said, CCX for close coupled extractive, that works really well for high temperatures. We have different probe options that allow us to operate at 1600 degrees Celsius and lower. We also have the capability of 4 measurements: excess oxygen, combustibles, methane, and flow. So those 4 measurements, which allows you to detect for any amount of plugging. But the challenge is because of that aspirator pulling that sample, you can only handle minimal loads of particulate. And higher loads pose a higher risk of plugging. And so even though you have the flow, you can also, even though you can monitor flow, you have the risk of plugging more often. Now I want to contrast that with the convective type. It's also suitable for much higher temperatures, okay, up to 1528 degrees Celsius. But the challenge, and also the challenge, okay, due to the speed within the convective type, there's no flow sensor, but we are capable of the added measurements of oxygen, excess oxygen, combustibles, and methane. And so those 3 measurements can be built in. So at high temperature, 3 measurements, and also the capability, the proven capability for high levels of particulate and even sticky particulate, even saturated streams we've seen as well. Okay, so far, Stuart?
So far, perfect.
So far, so good? Okay.
Yeah.
Well, if we think about the in situ type, there are some challenges. Limited quite often by temperature, believe it or not. And if it's not limited by temperature, it's because there's some water wash probe that makes it even more complicated. But it's very hard to get to that 1500 degrees Celsius point. The other challenge is it's only able to measure excess oxygen. So it's helpful in a number of cases, but you can't really see the progression of the combustion process or changes in fuel or other things that would affect the combustible measurements. So to monitor the health of so you don't have those added measurements to monitor for the health of the operation of the combustion process. Now, an in situ can handle higher loads of particulate, but there's nothing dusting it off. There's nothing. It's just in the process. So it's a challenge. And then finally, with the extractive type, it really depends. And with extractive type, as you see higher levels of temperature, as you see higher demands on particulate, you have much more complexity built into the process, much more complexity built into the system for the flue gas analyzer. So it could potentially handle higher temperatures. You could potentially have a rack with other measurements too. You could potentially handle much higher levels of particulate, but it's going to absolutely drive complexity in the design of the safety, design of the sampling system, and also the time and costs around that, let alone training. So advantages, certainly all these products have advantages, but in high particulate applications, we recommend and have designed the convective type for that reason.
Perfect.
And I didn't really say it, Stuart, but the HP stands for high particulate. So that HP stands for high particulate, and it's been proven in high particulate applications. It reduces that risk of plugging because it does not have an aspirator. It's more serviceable with that close couple design on the process flange. So even if it's on the process flange, it's more serviceable. Again, you have the other measurements like I mentioned, and other variants for hazardous area. So that's why it was invented, and I hope that answered that question.
Yeah, absolutely. Like I say at the beginning, I think, it's one of those things I've always loved about Thermox is that instead of trying to make that one analyzer fit all applications, you just make a different analyzer. I think that's exactly it. So this is designed specifically for those applications. And then we don't have to try and juggle it to fit. There's a couple of questions. I see one in the chat already, and we'll answer it in a minute. But there's also a couple of questions that come up quite regularly because you have a lot of different flavors. And which one do you pick? Which one do you use? Yep. Do we use filters? Do we not use filters? So we'll address those as we go along, I think. But so that from a selling point of view, you have to be a little bit more knowledgeable, I think, because there are more than one option to take out to the market. But it's certainly a much better way of doing things, I think, that you can say, hey, look, we're not just trying to make this thing work in your app. Let's pick the right analyzer for the right job. Mm-hmm. Perfect. Thanks, Tim. Yeah. So, I guess that leads on to my next question, which is on the next slide, which I know is coming up. What are those target apps then? Obviously, and I know historically the HP version, the predecessor to the one we're going to talk about today, has been out quite a bunch of years now, and and has been quite successful. And I know certainly from a Novatech Canadian perspective, we have a significant install base of the original HP IIC, so we know where those target apps are. But I'll let you describe it to the team online.
Yeah. So I said high particulate. I didn't say some particulate. So right. I want to make the distinction.
Good point.
Because when we talk about high particulate, we talk about like cement and lime, the kiln. We talk about pulp and paper, the black liquor recovery boilers. When we talk about wood products, we talk about like the wood processing furnaces. We also talk about when the power industry for the coal-fired power boilers, biomass boilers. We've also seen instances for refining in those steam applications. Some steam boilers for refining. There's also a number of instances in thermal oxidizers where there becomes heavy particulate depending on what you're incinerating. Mm-hmm. Also carbon black multi-hearth furnaces. Again, you need a measurement type of those environments, as well as reheat furnaces for steel. So we have had a lot of success in high particulate applications, and also these are the very high particulate applications. They're not some particulate; they're very high.
Yes, yeah, and not, to me, what strikes me on this list is not just high particulate, but that sort of sticky, it's not a clean, powdery particulate. This is gummy, gluey kind of stuff, stuff that's a problem once it gets in your lines and starts messing things up.
Yeah, black liqueur, yeah, even lime kilns. They could be burning anything. I've seen the list.
Yeah, exactly. Yeah, these. If you wanted a list of challenging apps that are out there, these are them, right? This is it for sure.
I hope that answered that question.
Absolutely. Of course it does. And I think this lends into this one, which is a question we get a lot now, particularly in the advent of AMETEK making one. But, there are others out on the market that have made blowback analyzers in the past. So that ability to, that ability to sort of say, we know it's a problem, but we want to try and eradicate it off the end of the probe by using blowback is one way of doing it. And AMETEK have a version of that. Mm-hmm. So where do we where do we see that fitting in then with the HP? Which way would you go if you were to advise people? Which one would you
Yeah,
pick?
yeah. I think it's a very, very important question. And the short answer is it's actually a spectrum, right? So blowback has a very specific role that it fits. It was originally designed within the space of coal-fired power to help with fly ash reduction. And in those cases, what we found is that blowback is really good with those dusty particulates. I say dusty because it's dusty particulate in the sweet spot of less than about 30 grams per meter cubed. Now, it's helpful because it can certainly blow off and dust off the particulate at certain intervals. It's nice because you can automate it, you can program it, you can set a blowback cycle in many different ways and configurations. And when we recommend it, it's for those dusty type applications. As I said, it was originally designed with the context and testing in coal-fired power. Now, the WDG-HP and the HP2, its predecessor, that's everything else. That's all the other particulate. That's all the other high loads, sticky particulate. And where while the W5 blowback has an aspirator, because it has a W5 attached to it, while that has an aspirator, that's also pulling in particulate too. It has a filter, but it's also drawing in and having a lot of particulate potential accumulate on it as well. So that's why it's important to have the dusty particulate to make it easy to blow it off. For the HP2 and for the WG-5HP, that aspirator, without having an aspirator, has a much slower flow, and that slower flow allows it to draw a sample without creating a massive suction. And so where we found the sweet spot is certainly above that 30 grams per meter cubed and much higher levels. We've even seen the HP2, the predecessor of the W5HP, handle saturated water streams after scrubber. So high particulate load, sticky particulate, and also even saturated streams in a number of cases. And just to give you a preview, so this is just a view of the blowback that was used for a WSCS application supporting coal ash. So it certainly has a place that works really well for surfacing, as you can see with the removal of that spot to be able to access the probe. Just one way to put it in perspective. Is it dusty? Is it extremely high? Is it high or is it extremely high? That's how I think about it.
From a Canadian perspective, we have we're not the only place in the world that gets super cold, but certainly I've learned the hard way as a European coming to this country that the cold temperatures can be somewhat insane. So cold spot and keeping the analyzer up above dew point is obviously a critical concern for us. It might even be our number one concern in a lot of our applications. And in your picture there, inside is great. So we've got blowback, it's inside. We don't have to worry about the cool air coming in. But one of our problems with blowback, as we found out in Canada, is the moment we've used the chamber up on the inside of the blowback, then we're sucking cold air from the instrument air. And when cold air in winter is extremely cold air, and we end up with dew point concerns. So for us, we're sort of somewhat nervous about it, unless it's an indoor app, as you say. And that's sort of what I like about the HP is that we keep it as close as we can to the process, keep all the temperature up, we slow the flow down, we try not to bring the problem into us in the first place. So we historically, you can see the sales of HP across Canada have been fairly large, and I suspect it's probably because of that. It resolves an environmental issue, if you like, from the Canadian perspective. The other one that's interesting, and I'll pause here to answer that question, and perhaps you and I can answer it together. But there's a question in here from Dustin at Synovus about probe filters.
Yeah.
And what is interesting, I think, from an industry point of view, is almost everybody else tends to always put a filter on the end of their probe, even under regular circumstances with their close coupled ones. And I think perhaps you could, verify this for me, Tim, but I think it's because most other people have very, very small bore tubing, and their analyzers run directly through all the process. So their aspirator sucks right through their process, through their sensors, and the tubing is quite small. So they're terrified about getting anything into the analyzer. So one of the things I like about Thermox is that with this fast loop concept in the bottom, we can tend to be much more open probed for a lot of our applications, which is somewhat unusual. So we're quite happy that we can handle a little bit of stuff coming in through the fast loop around the J tube and out, and then the convection loop can lift a relatively clean sample. I think that's probably the answer to why we have less probes on the end of a Thermox than other people do, but perhaps you could verify that.
That's exactly why we have less filters on the end of a traditional Thermox. And just emphasizing that So when I think about filters, I mean, I think about, okay, well, what's the particle size and what's the level of particulate? Because it's important, right? It's important if there is a, you
100%.
could, now over time, you will have potential plugging of that filter. And that's why we have a flow detector, flow sensor in the standard WG5 to monitor for that. So it is something that we do offer and consider for lower particulate levels. But the thing is, with an aspirator, you're pulling that sample through the filter. So over time, that filter will become, I wouldn't say plugged, but it'll start to cake on. So
Hmm.
it will have to be cleaned off.
Yeah.
And like you said, part of the advantage of that two-loop design, I didn't make a big stress about it, but it is very important. That fast loop allows particulate to come whip it in and out.
Hmm.
And that convective loop, because it's a fast loop, it protects the convective loop from massive particulate buildup.
Yeah.
Kind of, it's an offshoot, right? It makes a much harder angle for
Yeah.
that particular to go up as opposed to right in and out.
Yeah.
And so that's something that we found, and that it certainly is an advantage for handling some particulate without plugging up the analyzer, plugging up the filter. And as you mentioned, we also have bigger uh, a pipe tubing, if you will, within the
Internal
analyzer
tubing.
that helps a lot from allowing it to whip right out.
Yeah, yeah, I think it's a really good point because as you look around the industry, again, it's a bit of a unique feature of the Thermox that it does it that way, and that is the reason why we have a lot less filters on the end of our regular probes. But and again, I know there's a question at the end about serviceability. All analyzers end up with a little bit of servicing requirement. That's just the nature of the business. And again, I think AMETEK, you'll show it later, but I think AMETEK have come up with a design and say, look, okay, if it gets in, this is how we clean it. It's not impossible. So there's a question there, but I think hopefully, and we can talk about it some more, Dustin, another time. But hopefully that answered the question that you're unlikely to see under normal circumstances a filter on the end of our WDG-5 standard range. But that said, the HP always has a filter on the end, correct, Tim? We always have a filter on the end of our probe
Right.
for HP.
HP. Yeah,
Yeah,
HP does.
yeah.
Same with the
Okay.
yeah, yeah. The other same with the blowback. The other nuance is, like, again, I want to make the distinction between some particulate, high particulate, extremely high particulate. So it's just,
Right.
if there's a concern, then that's the buckets I think about.
Right. Yeah,
Yeah.
100%. Okay, perfect. All right.
Yeah. Great question, Dustin.
What
Okay.
we got next? What's up next?
All right. So
All right, well, that's perfect. This is good timing.
yeah.
It's I, I'm paid to be biased. I say this to all the customers, all the guys that I know online here will have heard me say this many times. I'm paid to
Yeah.
be biased about Thermox, but truly, having worked for three of the other majors over my time in the industry, it is by far the best analyzer as far as I'm concerned. And I think what's interesting about the 5, although we still consider it new, it's been out 10 plus years now. It's a unique design that no one else has quite followed yet, and I'm always surprised by that, because it's added some features, it's added some design, got rid of the controller idea. All of these things are incredible to me, and they're universally loved, I think, by most customers. But so it's exciting then that now, over the last couple of years, you've worked hard to get us out a new version of the HP that adds those features. So let's talk about that, because I think it's interesting, some of the new stuff that's coming out with the HP that resolves some of our frustrations with the older models.
Yeah,
What's
absolutely.
new? Tell me what's new. Tell us all what's new.
Absolutely. And I'm happy to introduce the Thermox W5 HP. Happy to introduce it. So what's new? There's a lot of things, and I'll kind of go into some of those details, and you'll see the word new here on this as well. But so what's new? So we have certainly a new furnace. That furnace is similar to that of the WG5. So smaller cells, tighter, makes a much more precise measurement, and also monitoring for the measurement itself. So new furnace, new combustible block, better stability of the combustible measurement to uh, maintain uh, maintain temperature. As you maintain temperature on the combustible block, you also maintain accuracy. So stronger accuracy on the combustible block. We have the WG5 electronics, which has the redundancies and the diagnostics and the proactive alarms that you see in the standard WG5, that we're really happy to share and bring over to the 5 HP. Also, we recognize the importance of having a loss of pressure switch in a nice convenient place for all groups, and has various locations for all, groups and so on. And we also have the option for a new loss of pressure switch inside the electronics box. So you can handle groups A, B, C, and D for class 1 to 2. So that's a quick glimpse of what's new, what's inside the product. And then if I wanted to expand, how does it compare to the HP2, its predecessor? There are a lot of things that are similar and a lot of things that are slightly modified, like I mentioned. So what's similar about it is it's the same principles of close coupled convection, like we had for the HP2, the predecessor. Same response times, same furnace, parameters, if you will. Same probes and filters. So if you have probes and filters for the HP2, you could reuse it for the WDG-V HP. Also the same limitation on probe length because it's convective. It's a convective type of analyzer. It's a slower flow. You don't want to make the probe too long, the probe filter too long, where it wouldn't be able to make a suction in 3 meters away. So it's limited by a 4-foot or a little bit, meter and a half, a little bit less than a meter and a half length. But that allows us to make sure that that convective type can pull in a sample. That being said, those are all similar. Things that are slightly different, I say slightly because I want to make an honest assessment. What's similar, what's different. So what's slightly different is if you look at where the hole is, where the probe fits, okay, it's actually a little bit, the bottom of the analyzer is slightly lower compared to where the standard HP2 is. So just something to keep in mind. We have different options for fitting the WDG-V HP into any installation, but something we think about, something I think about. We also have different manifold blocks. So that block that's connected the probe to the process, that's slightly different too. So it could not be reused, but it's something that is there. Now, things that are different, as I said, the new furnace, WDG-V style furnace, new electronics using the WDG-V electronics, new combustible block to make sure that there's better stability, thermal stability for that combustible block. New combustibles and methane detectors, that's also new. Just mentioned like the internal loss pressure switch and the added serviceability improvement around removing that probe and filter. Now, things that are not included, like that are on the standard WDG-V flow sensor, again, because of flow, lift-off version to standardize on the more thermally sound WDG-V HP enclosure. No flame arrestor because of flow, and also no, not currently still certified. That being said, what isn't is not included. As I said, there's a better enclosure for the WDG-V HP, better ingress protection, keeping it in those cold areas in Canada, like you mentioned, but also better ingress protection from the elements. Again, the options for combustibles and methane as standard options. Hot wire detector always standard for those high severe service, even high sulfur applications. Greater serviceability, WDG-V electronics. Does not include the lift-off version, like I said, the flow sensor and so on. We can certainly make it versions for Haskell AC for highly chlorinated applications, high dew point versions. We can do that too as a custom. We've done a number of those already, and also floor mount variants if you need it for a nozzle that's on the floor. We can also do a custom order for that too. So I say that because that's what's new, and also that's what's included, if you will. So I hope that answered your question.
Absolutely. Yeah. So then, obviously the lead on question here, and perhaps you've sort of covered up on a lot of it already, but, then what do we get? What are the advantages then of, what does that get you? What are the new features,
I should have just answered that question before in the last one, but
they kind of lump together, right? But it's, that's okay. You've explained what we've built, what Thermox has built, okay. So now what does that get me? How much further ahead am I here?
Stuart, well, that's what's new. Okay. What are the advantages? What's better about it? So I mentioned improved serviceability. So you can see those 4 bolts right here. You can take out that entire manifold block. This is the manifold block. In the past, the previous generation model, you would have to take the whole analyzer off the process in order to service it. Okay, well, sometimes the analyzer weighs 30 pounds, sometimes the analyzer weighs 55 pounds, sometimes the analyzer weighs more than that. That can be a challenge, especially in a high particulate application. So improved serviceability, built off of this 4-bolt pattern for the manifold block to make it easier to access. Also, like I said, a greater combustible stability because we have a bigger thermal mass for that combustible block. It can maintain temperature better. And it's also easier to change out. It's easier to change out with the WDG-V style detectors. So you can more easily access it compared to the HP2. And then finally, the advantages of the electronics. It's the same board as the WG-5, standard WG-5. And so as such, it uses the capabilities with the AMOVision, capabilities with predictive diagnostics, the proactive alarms. A lot of the things that we considered in designing for SIL are embedded into that software and the software as well as the board. So it's all kind of built in. Also, it's Class 1 to 2 certified right out of the box, and also ATEX ICX certified. So happy to share that as well. So I hope that covered the advantages to it, but let me know otherwise.
It does, and I think, I think obviously as we step forward with the industry in the last, say, 20 years, let's say, the combustible stability is the big bugbear of the industry. And, and let's be fair, everybody has struggled with that, with stability in the combustibles, partly because, we're getting better at combustion control. It's a good news story in one sense that we are people are paying much better attention to trying to lower their combustibles output, CO outputs, and have better control on the efficiency of their furnaces. So we are tweaking all of our measurements down as low as we possibly can, so that's the story of stability, that story of not having interconnect cabling anymore, that story of the thermal mass, all of these things that we can't do a great deal with the actual technology itself, but we can do everything around it to physically try and make it better. I think is a very good news story. It's improved readings all around, I think, as best we possibly can under the circumstances.
Yeah, and just kind of simplifying it, it's a tighter measurements as well as with that stability as well as serviceability.
Yeah, 100%. Yeah. Okay, I think that is our next question, the serviceability, right? We people in analyzers, and certainly it's always a fatal mistake of analyzer manufacturers or sellers like us to overstate, there's no maintenance, you'll never touch it. It's always a dangerous thing to say. I think it's better to say, look, most process analyzers have an amount of service requirement, depending on the application, depending on where they go, depending on where there's many factors for all of that. So it's better to hit it face on, and in combustion control, serviceability is a big deal. It's how do we keep these things up and running? They're often critical service. Sometimes they're even in control mode, so how do we keep these things running as best we can and predict that as we go along? I guess that's the big question here.
Yeah, I appreciate it. And Stuart, it's one of the things where the HP design was designed because of high particulate. It was designed because of these challenging applications. And I'd love to say, hey, I'd love to say that it could work in any case without any maintenance. That's where we see limited maintenance is in like semiconductor, where it's clean room.
Right.
If you contrast that with black liquor recovery boiler, like this is a very different scenario, right? So there's different high particulates and different things. So
100%.
So handling that, one of the things we wanted to focus in this design of the WG-5 HP is how do we make it easier to access to clean and probe the filter when you need to clean and probe the filter. And I mentioned it in this earlier slide, like we have this, we have the manifold block, right? We have the manifold block right here. Well, that manifold block was a challenge in the past to access, and also we'd have to confront the fact that a lot of people would have to take the whole analyzer off the process just to change the filter. I say just to change the filter because we're talking high particulate application, and you have to change the filter. Okay, every time you had to change it at some point, and that's a big challenge. And so people would have to, a lot of end users would have to change the filter and take the whole analyzer off the process. So the manifold block is a lot more accessible, so that you can put a wrench to it and actually take it off. And I have some pictures from the manual just to make it easier to see, also to get you ready to see, okay, well, what's in the manual? This is what's in the manual. So a couple of things. To even access it, we have, before you do anything, before you even take it off the process, right? You have to get to these nuts right here just to take it off. So we have this little hanger that allows you to put the furnace, put the combustible block on a place while the wires are still connected to the board. Okay. It's a simple little thing, but you don't have to rewire everything just to take it off the process. Okay. We don't want to have to do that. So it's easy to remove and disconnect it from the internals. So you can have it wired up to the electronics board and put this on a little hanger. And it's a silly little thing, but it helps a lot for accessing it. And then by disconnecting right here, you can then remove the manifold block. You can use those 4-bolt pattern and make it easier to isolate and remove that manifold block. This is installing it, but if in the same idea with removing the probe and filter. And then after you clean the filter and clean the probe and you put on a new one and clean it later, you can reinstall it by reattaching it, sliding right back in to the assembly. And as you can see, the furnace is still hanging here, and you can rebolt with easier access. So one way to make it easier to access the probe and filter, and also easier to reinstall without having to disconnect everything. So how'd I do? Is that helpful? Is that a good answer?
Yeah, it's awesome. I think that's important. We have a lot of applications where these are outside, they're up in the air, and the catwalk is 3 foot wide. And taking the analyzer off is awkward, requires more than one person usually, and there's not a lot of room. Even pulling a 3 or 4 foot probe across those is somewhat awkward, but at least it's manageable. And and usually a one-person job. That helps with limited resources on the sites these days. So I think it's a very clever design. That deals with the practical nature of what we have to deal with, for sure.
Okay.
100%. Thank you.
So
This is a good question, Tim. And I think in theory we could have put this at the beginning. Why are we measuring flue gas analyzers? But I think it's nice to put it at the back end, partly because of the practical nature of how we all end up in our careers and our jobs. Very often for technicians on site, you just start working. You just got to get out there and you've got to start doing your job. And you'll inevitably end up doing combustion control very quickly because there's so many of them, especially if you're in the hydrocarbon business. So you end up doing it, but then it might take you some time. You back it up and go, well, what is the actual point of this analyzer in the first place? So I kind of like to put it at the end to say, look, everybody knows these analyzers. Most people have worked on them already. But maybe it's a good time at some stage to stop and say, well, what is the value of this? Why am I actually doing this? Why do we have so many of these on our plant? So maybe you can answer that.
Yeah, and it's one of those things where maybe you have an HP2 on an analyzer, and you're like, well, okay, well, great, we can upgrade, but why are we even thinking about maintaining and servicing this this measurement in the process? And so the way to just make it hopefully really clear is really comes down to safety, efficiency, and quality control. Really specific to the industry, but quality control too. So from a safety side of things, the oxygen measurement by itself, that excess oxygen measurement provides the correlation to the air-to-fuel ratio to the burner. So that you have extra air at the burner, knowing that you have excess oxygen in the flue gas. That's helpful. That also correlates with the air-to-fuel ratio. So excess oxygen provides that set point for combustion air and fuel to burner. So that's a safety thing because you have safety margin at the burner with the air. Well, also with a combustible measurement, you can monitor for combustible breakthrough. You can monitor for high combustibles. You can monitor for the risk of an unsafe condition with that combustible measurement. Because as you start to see it increasing, that's a signal that something's happening. And above certain thresholds, action needs to be taken. And then also, we've seen with our standard WDG-V, but also just with the measurement of methane to prevent unsafe conditions, prevent fuel-rich conditions from flame out, in some cases tube leaks, or also just process-related issues. You can have a methane detector before a electrostatic precipitator to reduce the risk of explosion because you can monitor for methane, other hydrocarbons, without it getting to that point of the electrostatic precipitator. So that's something I think about. It's really important. I'll go into that in a little bit more detail in just a second, but that's just something I think about when it comes to the methane detector. A lot of people wonder, okay, so carbon monoxide and hydrogen are combustible, but why is methane not included in a combustible detector? There's some nuances of the technology, but to get a good measurement for carbon monoxide and hydrogen, things that are incomplete combustion, it really helps to have a separate detector for combustibles and a separate detector for methane. All that said, keeping them separate allows you to monitor for safety at different levels. So safety at the combustion air side, safety at the combustible breakthrough side, and then also safety for a hydrocarbon flame out type of scenario. So that's the safety side. On the efficiency side, I talk about it a lot, but the concept of optimized combustion. How do you optimize combustion? How do you find that sweet spot where you don't have too much excess air and also where you don't have enough. And so combustible detector allows you to find that sweet spot to reduce excess air levels safely. By reducing excess air levels, you also reduce your carbon dioxide emissions, your NOx emissions. You also have a cost savings by reducing the fuel. So all these things working together, more efficiency, meaning less excess air at the burner, means less emissions, means increased fuel, which means a fuel savings as well. So less reduction in fuel savings, right? Reduction in fuel consumption. The other thing is quality control, and quality control really depends on the industry. But the one thing I want to highlight is that in cement, high sulfur coal operations close to stoichiometric can avoid contamination by SO2. In the steel industry, it is important to have lime used as a neutralizing agent for SO2. So different industries also benefit from a quality standpoint, making sure that their combustion process is in the right range. I don't know if there's anything you want to add to that, Stuart, but that's just how I think about it. And that's why we would start. That's why day out why monitor flue gas.
Yeah, 100%. Like in my simplified version of explaining analyzers to people over the years, I always think that we could effectively put all analyzers into one of three buckets. It's either the process reasons, efficiency and process control. It's either safety, either the plant or the people. Usually the plant before the people, sadly, but at least now the people, and then the environment. And what I love about combustion control as a concept is that if we do it right and we take a lot of pride in getting it in the right place and doing the right job, we're sort of ticking all three of those boxes at the same time.
Yeah,
we're maximizing our fuel burn, we're making it safe on the plant, and we are reducing our emissions to as low as they can be. So you sort of tick all three at the same time. That's what I love about doing it the right way.
Yeah, and I really appreciate the safety element, and that's why I keep emphasizing how much. And speaking of it, go ahead.
I was going to say I was always amazed that we had a statistic I know at Thermox about the number of explosions that take place across North America in plants. It's still a significant number. Obviously, doesn't get reported greatly, but it is still a significant number of incidents that take place, and it relates to not being in control.
And that's one thing I want to highlight. Actually, is just one example of high particulate application, electrostatic precipitator. Just having the visibility, the full visibility of the combustion process. And so a lot of equipment, even it starts up with natural gas, and you can have a combustible measurement with the analyzer on. That's not going to see methane. And so having a combustible detector helps for normal operation, but it's not going to respond to methane. And so having a methane detector to monitor for light off, for purge cycles, can really protect the downstream equipment from some type of unsafe conditions. So really having a way to have a precaution to monitor for flame out or a ignition that hasn't been purged suitably. So I really think about it as how do we provide that option and opportunity for full visibility of the combustion process. How does the excess oxygen, combustibles, methane work together during startup and also normal operation?
Yeah, 100%. Perfect. Thank you, Tim.
I think we're getting close.
I know we're running a little short time, and we do want to leave a little room for a question. So, but maybe you can answer this last question as briefly as you can, perhaps. What are some of the best practices then when you're thinking about this particular area of the industry, this high particular area that we've been talking about?
Yeah, there's a couple of things that we've seen in different applications, different industries, and just to simplify it, direct measurements helps a lot. Making sure that you have less risk of ingress air biasing the measurement. If you think about it, we're measuring oxygen. Oxygen can be biased by having air leak into that process. So having a measurement on the process helps. So a direct measurement on the process flange. Why we have this close coupled convective design. That's one thing. Also, that can be used with the WDG-V HP. Also, a sample conditioning system, that would be a different type of technology, more of a extractive or close coupled extractive type. Water rush probes, water cooled probes, we've seen that they support different applications for high particulate. And then also, so that might be more for like an extractive type. We have different versions of the WDG-V, if you will. Then also a bypass system is something that we've found as well that enables measurement even in very high and difficult and I would say stressful, but very high particulate, very intense and severe applications. So just to give you an example of what a bypass system might look like, which we've even used with the WG-V HP and the WDG-HP II, its predecessor. There are different ways to bypass the measurement. With a vertical probe, you could have if there's a kiln here, you could have a separate tube that draws a sample. And what's drawing the sample? Well, there's a induced draft fan downstream that kind of pulls the sample, and that gives access to the analyzer to make the measurement in a separate space without being right in the middle of the front of the high particulate. So that's an example with a vertical probe. You can also do a horizontal probe too. That's an example as well, where you have the process, the kiln in this case, pulled by an ID fan that allows you to make a measurement and back to some other place in the process. And you also have the ability of blowing back a separate air to force any type of plugging a particulate out that way. So just another example of a horizontal probe bypass. And then another bypass would just be a bypass box, and just a way to get, again, in very difficult applications like a kiln, have a way to draw a sample in and make a measurement to the analyzer, put it downstream. This is an example of a bypass system and a knockout box that we had with WG-V HP, as well as the predecessor of the HP II. And they're on both sides of this little knockout box. And there's enough ducting. This is the induced draft duct, as you can see, to this fan out here. And the way it went was from the kiln up to this knockout box. And then we're able to even validate them side by side as we were doing the original testing.
Sure looks like a high particulate application there. Look at that place.
Oh, yes. Oh, yeah. Very hot too.
Yeah, and dirty. Yeah, for sure.
Yeah. So, Stuart, I hope I
awesome. Tim, that was great.
And
like I say, we'll collate that for everybody into a PDF format, so anyone is welcome to have it. And I think it addresses most of the questions I get coming across to me. It's a great sort of way of breaking it down rather than just presenting it all. Say, okay, well, this answers this point, this answers this point as we go along. So that was fantastic. It's really great. We've got like 5 or 6 minutes left. If anyone online has any additional questions for Tim, please raise a hand or speak up. I guess Garda will open up the lines here. Maybe you just did a fabulous job, Tim, and we answered everybody's questions all in one hit.
Okay. Well, that was a great question earlier about filter. I definitely appreciate the nuance of the filter. And again, the WG-V HP has a filter. It has to reduce risk of plugging. Again, there's a flow. We want to prevent it from plugging. Same with the WG-V blowback. That also has a filter, just so we're not pulling in particulate that would plug up the internals of that blowback system.
Yeah.
W5, again, that's a nuance. It really depends on how much. I would put filters in the some particulate category as opposed to high particulate category. Really, but that was a good question.
And I think again, I think that's what having worked around the industry for a long time, as we both have. I think that it is worth stopping to talk about these things because AMETEK have a number of different ways of doing things. So and that question of filter or no filter is quite a common one because unlike many of the others, you don't see so many of them. Most people have them on there. So, the floor mount being custom, does it still have the filter removed by removing the manifold block if you're on the floor mount?
On the floor mount.
Can you hear me now?
Yes, we can hear you.
Yes, we can, Robert.
Okay. Yeah, these computers suck. Anyway, I just wanted to commend you on an outstanding presentation, both of you, and I want to be sure that I get the PDF, sent to me via email. Thank you.
Well, we'll make sure for sure. And we're happy to see you here. We know your credentials in the industry, so very pleased that you would think that of us. Thank you.
I actually worked with Don Sales back in about 1973 on this analyzer.
There you go. That was probably a 2, WDG-2, probably back then, hey?
It was a WDG somebody.
Yeah, well, we appreciate it, Bob, and for sure we're happy to share. So we'll send you a copy of the PDF.
Thank you again.
Version. You're welcome.
Thank you again so very much.
Thank you,
Thanks for
Bob.
joining.
Okay, so we got a couple here. We got the one about floor mount, which I'm not. Do we do a floor mounted version of the HP? I guess that's the question.
Well, again, that's a custom. And the short answer is what happens is the manifold block is accessible on the floor. So that's a very good question, a very interesting nuance. So the box is longer in order to fit the manifold block there. But
Right.
the same idea of putting the 4 bolts there so it's easier to access and then pulling it out that way.
So you can take it out of a floor mount effectively.
Yeah, that's yeah.
Yeah. Okay, perfect. And then there was a quick question about SO2. So I'm guessing it's, how about SO2? I'm guessing it's at what levels can we handle?
Yeah, that's a good question. It really depends. And I say it depends as in, so our zirconium oxide cells, it depends because we can handle a lot of different types of sulfur levels. The challenge is just how high, because above a certain length, it'll just reduce the lifespan, the short end. So you can handle higher levels or spikes. The challenge is that it just poses the risk of reducing the detectable lifespan. That being said, typically around less than 1500 ppm SO2 in the flue gas is what our target is. Less than that. If it's higher, we can handle that. We've handled much higher. There are different accommodations we've done for very high. That's where high dew point analyzer comes in.
Yeah.
When we start to think about the dew point exceeding 200 degrees Celsius, 180 degrees Celsius, we start to think about the high dew point version. Not them certainly, but something we can do. That's the only stipulation. Aside from that, from our combustible detector standpoint, that can also handle about 1500 ppm of SO2 as well. We've standardized on the hot wire detector, so that's able to handle high sulfur levels. We just above 1500 is where we start to
right.
That's where it starts to draw the line, right around there.
And, and that's a good point actually, that we have these severe service higher versions of for SO2 content. We'll actually change the internals slightly, right? Of the analyzer to be able to accommodate more complex measurements.
But if they're seeing percent levels of sulfur, we'd remove the combustible detector, and it'd be oxygen only. In that particular case, we've done it. We can do it. It's that's the high dew point version though.
Right.
And that's where so. Long answer to the question, it becomes at some point it becomes a high dew point version. It's oxygen only and capable of just that design.
Yeah, 100%.
Good question. You see anything?
We're cognizant of the time. We've run over time, but if anyone's got any last minute questions for us, we'll hang on here for a minute. But if not, we just want to say thanks to everyone for being here. We appreciate you giving us an hour of your time. Hopefully it was useful. If anybody wants a copy of what we've done today, let us know. Either just in the chat, you can leave a yes, no, or you can contact us afterwards, via the link, and just let us know. We're always happy to share. Tim and I, we're more than happy to do that. So we'll PDF it. Otherwise, it'll be an enormous file. But other than that, you're very welcome.
Right.
Okay. Thanks, Tim. We, as always, it's always a pleasure hanging out with you and talking about products. We'll do it again sometime. Why don't we say that right now? We'll come up with another reason to do something like this. I think it was fun. Thank you.
That'd be great. Thanks for inviting me, Stuart.